Hello guys, we meet again. I'm Juan and I'm from Team Pressure. Today I would like to present one of the topic in engineering mechanics 2, which is planar Newton-Euler dynamics of rigid body. Generally, the dynamics of a rigid body in general motion combines both translational and rotational motion. For translational motion, we already have a balance of linear momentum, which can be solved by using summation of F equals to ma bar. But how are we going to solve for rotational motion? Thanks to Euler, because F gives us a balance of angular momentum. This can be presented by mg equals to ig alpha, where this angular momentum with respect to the center of mass g. For a fixed point O, we can define by MO equals to IO alpha. Meanwhile, to sum of moment about another point P that is not fixed and not the center of mass G, we must use this equation, which is MP equals to I bar alpha plus MA bar R, where R is the distance from P to G in the direction perpendicular to A bar. To make it more clearer, these two equations can be presented by these two diagrams. Generally, for the summation of F equals to MA bar can be presented by free body diagram. However, for the summation of Mg equals to I bar alpha, we can present it by kinetic diagram. For the free body diagram, the plane has been acted by the external applied forces, which can be presented by F1, F2 and F3. For the kinetic diagram, we can see that there is a moment about point G is equal to I bar alpha. Now we have done with the introduction of the planar Newton-Euler dynamics of rigid body. Let us move to exercise. To get a more clearer view about this topic, we will be going through one question. In this question, we can see that a metal hook with radius of 150 mm is released from rest on the 20 degrees of inclined plane. If the coefficient of static friction and kinetic friction are given by μs equals to 0.15 and μk equals to 0.12, determine the angular acceleration alpha of the hook and the time t for the hook to move a distance of 3 meters down the incline. So the first thing that you need to do when you got this question is drawing a free body diagram and a kinetic diagram. So I have drawn free body diagram and kinetic diagram for you. In this free body diagram, you can see that the unspecific weight of mg, the normal force and the frictional force acting on the hook at the contact point C with the incline. Meanwhile, in the kinetic diagram, it shows us the resultant force ma bar with g in the direction of its acceleration and the couple I bar alpha. The counterclockwise of angular acceleration requires a counterclockwise moment about point G, so F must be up to the incline. Now, we are going to assume that the hook rolls without slipping, so we can say that A bar equals to R alpha. Then, we will be used the summation of forces in x direction equals to ma bar x. We will get our first equation, which is mg sine 20 degrees minus f equals to ma bar. For the summation of forces in y-axis equals to 0, we will get our second equation, which are n equals to mg cos 20 degrees equals to 0. Next, apply the balance of angular momentum. We will have Fr equals to mr squared alpha as our third equation. By eliminating F in the first and third equation, and the substitution of kinematic assumption of A bar equals to R alpha, we will get this equation: A bar equals to G over 2 sine 20 degrees. Now we get the A bar, which is equal to 1.678 meter per second squared. Alternatively, with our assumption of A bar equals to R alpha for pure rolling, we can take a sum of moment about point C equals to I bar alpha plus MA bar D, which will give us this equation, and finally get the same result for A bar. To check our assumption of no slipping, we calculate F and N and compare F with its limiting value. By knowing the value of A bar, we can simply get the value of F from the first equation, which is equal to 0.1710 mg. We also get the value of N from the second equation, where N equals to 0.940 mg. For the maximum possible friction to occur, F max equals to mu S N, and we get the force max equals to 0.1410 mg. Because our calculated value of 0.1710 mg exceeds the limiting value of 0.1410 mg, we can conclude that our assumption for pure rolling was wrong. Therefore, the hoop slips as it rolls, and A bar is not equals to R alpha. The friction force then becomes the kinetic value, where F equals to mu Kn. Thus, we get the value of F equals to 0.1128 mg. Next, we substitute the value of F equals to 0.1128 mg into our first equation. Then we get the value of A bar equals to 2.25 meter per second squared. In order to find the angular acceleration of the hoop, we use back our third equation by substituting the value of F equals to 0.1128 mg. Thus, we get the value of alpha, which is equal to 7.37 radian per second squared. Next, to find the time required for the hoop to move a distance of 3 meters down the incline, we will use the kinematic equation x equals to half at squared. By rearranging the equation, we get t equals to square root 2x on A bar. By knowing that x equals to 3 meter and A bar equals to 2.25 meter per second squared, we get the value of time for the hoop to move a distance of 3 meters down the incline is equal to 1.633 seconds. Now, we have already done with the question. The reference book that I have used for the presentation is J.L. Merriam and G. Crick Engineering Mechanics Dynamics 6th edition. Hope that this presentation will help you to get some overview about this topic and will be useful for revision, especially for second year engineering student. I think that's all for me. Thanks for watching. Bye.